Good evening to one and all. And in today's session, we are going to understand the basics of industrial automation and Industry 4.0. And also, we'll be having a demo session that will be on the industrial robotics incorporated with industry automation. And sorry for the delay which had happened. And I'll be continuing through the session for now. I think I'm audible to you. Please respond in the chat section if I'm audible or not, please. Yeah. Okay. Let me move on with the presentation part.
Yes, you can go ahead, sir.
Thank you, sir. This is what the overview of industrial automation, what we are going to see right now. We are talking about Industry 4.0 for a lot of period of time. Before that, we have to understand what is Industry 1.0, 2.0, 3.0, and what stage are we right now. And in certain countries, they are moving on to Industry X, so on and all. So what are these revolutions happening behind us? What are these revolutionary changes that are happening? So we are going to just see all these content in this today's session. And we are going to also see about the overview of industrial robotics, the input-output configurations, network systems, so on and all. And apart from that, the main overview of the session is that we are going to understand about the demo process also, how to handle the teach pendant, what is this teach pendant is all about, and what is this industrial robots are reacting, how it's working on with, and different types of industrial robot, etc. All these content we're going to see right now. And let's move on with the slide. Okay, these are the four industrial revolutions which we have been seeing throughout the sessions: the Industry 1.0, 2.0, 3.0, and right now what we are in Industry 4.0. Basically, this Industry 1.0 has started very long back in the 18th century itself, where the steam power is the basic ideology behind the Industry 1.0. Before steam engine, there were not many support systems which are incorporated with manufacturing, etc. So this Industry 1.0 made a greater revolution in the manufacturing and other parts of revolution, majorly in the economical process also, which where this Industry 1.0 has collaborated. Then in the later parts of 20th century, we have started with mass production in automotive using that is where this mass production has started, and which is called as Industry 2.0, where before that the mass production is not in a concept, and we have been using the SPM like stuff, only a specific part has been manufactured into. And the third revolution also in the 20th generation has been started, that is the PCB boards, the programmable electric circuits, computer technologies which have been incorporated, that we call it as Industry 3.0. And coming back to the Industry 4.0, we are into the robotics and automation process, where we involve robots, programming of robots, and industrial automation line, where it just uses to run the process in a very efficient manner. And that is where this Industry 4.0 is incorporated into. And this slide, you can see about the various parts of the country where this Industry 4.0 has been implemented, and where in the current situation is standing on. And 2025, China is looking forward for Industry 4.0, and right now Germany, France, Sweden, these countries are into Industry 4.0. Just growth initiatives which are taken by different countries has been mentioned below. You can see the countries in and around Germany can be clearly seeing their growths in Industry 4.0, and they are into the next generation of manufacturing also. And these are actually the core of Industry 4.0, where you can see the data exchanges between the manufacturing technologies and process, which includes cyber physical systems, Internet of Things, industrial Internet of Things, and cloud computing, and cognitive computing, and artificial intelligence. If you deal into each and every concept, it is a very tedious process to go on with. Just for understanding purpose, I'll be explaining each concept in a very easier manner. Uh, Sorry for the inconvenience. Just switched on the bot which is running behind me to run in automatic mode. Yeah. And this industry 4.0, we collaborate with a lot of support system, which is in the, as I said before, cyber physical system, IoT, Internet of Things, and Industrial Internet of Things. Most of you would have got this about Internet of Things. We are going to collaborate the data, and we are going to implement the parts. The industry Internet of Things is an interesting topic where we collaborate the missions into the IoT, where you get different kinds of inputs from the missions, like what is the peak production you are achieving, what is the minimum production you are achieving, at what time you are getting this peak achievement, what is the circumstances or the behavioral of the missions at various temperature condition, various loading condition, whether the operators are working in an efficient manner or the missions are coming into the time process which is done in a very regular services, getting you the great output or whatever it is. All the data are collected, and the AI behind the software runs the test, and it gives out the oblique output where you can acquire the data very clearly, and you can achieve very good production with the help of this IIoT, which is Industrial Internet of Things. And cloud computing is the basic thing which you collect all the data into your cloud wherever and whichever circumstances you wanted to utilize it. Whether the mission is there or not, you can utilize it with the other parts of this also. That is where the cloud computing is related. And most importantly, this artificial intelligence is a concept. It is purely based on the data, and the data is how it is incorporating to get out the premium outputs. That is where this artificial intelligence makes a big deal. Let's move on with the next slide. Sorry, there was a network glitch. Sorry. And this slide is a very, very important slide where you're going to see how evenly or how eventually these technologies have been drastically gone into the environment very easily. You cannot see the following first set of apps or the supports there in 2006. You can see smartphones. Nobody would have imagined they would be using a smartphone in everyone's hand in the year of 2006. Smart devices in the sense you can see this Google Mini or Alexa, or even your smartphone have your Google Assistants, even the Siri assistant from the iPhone. Those devices are not available in 2006. And you can see this Android. Nowhere we were using the, not we were, somebody would be, in the community would have used the smartphone devices, I mean these normal mobile phone devices in 2006, and most people would not have these mobile phones also in the earlier 2006. But right now, if you see, each and everyone is having their smartphones. Even the students at the age of 15, 16, they have their smartphones in their home. Not 15, 16, below ages also, some places they are having their smartphones. But in 2006, that was not the scenario. The Kindle by Amazon was not there. 4G, Uber, Ola, Airbnb, Oyo, WhatsApp, Snapchat, Instagram, nothing is available in the year of 2006. But if you take in 2015 to 16, in this 10-year of gap, in a decade, there was a gradual change or drastic change, and quantum jump was there in between the devices which we are achieving. So that is purely because of the systems, computing systems, which Industry 3.0 has been incorporated. There is one more survey which has been there in the second part, the time to reach 100 million customers. You see, telephone to reach 100 million customers, it took 75 years, nearly 75 years to reach 100 million customers. And the web, it took just 7 years. The web, the internet, it took just 7 years to reach 100 million customers. Facebook, it took 4 years. Instagram, it took 2 years. WhatsApp, in just 6 months, it reached 100 million customers. So that is how these stuff has been keep on increasing and how it has been gradually moving on to. So there is a lot of stuff just been focused on the quantum improvements going on into the market. So this slide is very, very important, where you can see the sequence of manufacturing which has been done in before. And this is the rigid sequence on a production line. Rigid sequence is nothing but the line will be keep on moving on. As you would have seen the previous session of mine, I would have shown you the Tesla's factory, where these Tesla's factory, the robots will be keep on working on from one station rigidly, but the conveyor will be keep on moving on for the other stations. But at the end output, you will be getting your overall process. This is where we call the sequenced car manufacture on the production line. After the sequence line also, though, there are much other line productions where there are drastical changes may be happening in the workstation process also. This is the factories which would be following in the futuristic work. These workstations will be on a different line layup. Wherever the workstation is free, the automatic process will be directly, it will be incorporated to the workstation and it will be directly outsourcing to the output. This we call it as machine-to-machine talking or machine-to-machine learning, where if one system or one robot completes its process, it gives signals to the other robots, where the other robots indicate to work on with the previous subjects. For example, if there is a line is running on in a workstation, if there is a glitch is happening or if there is any issue is happening in any single workstation, the robots will automatically shift their lane to the next generation of or the next robot, and it tends to keep on working. There won't be any stop or there won't be any break in between the processing of workstation. This is what the next generation of factories will be going to looking like. This is how the industry revolution has been happening into, and there are a lot more advantages and creative motors moving on into various revolutionary process that we are going to discuss in the forthcoming sessions. And yeah, this is what which eventually runs the industry 4.0. Basically the agility, the efficiency and innovation. These are the three basic aspects from industry 4.0 which drives the industry 4.0 into an efficient manner in following the developed countries, and which we are going to try to develop in the growing countries. If you take the consideration of innovation, it considers the value chain transformation through network processing objects. So it is the innovation is not just developed from anyone's mind or anyone's place. According to the work environment, what is needed in the current situation, the efficient solution will be able to compete with the innovation. That is where this is a cycle where efficiency comes into the process of innovation and it develops to the agility. Yeah, right now, before going into the next topic, we'll be seeing the industrial automation procedure or the process, where I'm going to take a tour over the automation process through the mobile phone. I'll be reconnecting with the mobile phone so that you can understand how this automation process, which in CIT will be working on. This is a miniature of the process of the whole line setup, where you will be having hydraulics, pneumatics, and the support system of the robots, vision mission system, everything is available. I'll be just getting a tour over to the facility. Later in the session, we'll be having the demo part also. First, I will be getting a tour overview to the live session. Just hold a minute. I think you can able to see the session over here, the facility. Yeah, this is our automation facility. This facility, what you're going to see is this is the controller of the automation facility. What we have collaborated from Japan and China to inherit this facility, where from the raw material to end products, you can go through the through run without any human intervention. That is what the objective of this facility, where we have the Mitsubishi PLC and Mitsubishi robot, and this is the Mitsubishi PLC, where which supports the all the pneumatic support which is required in the system, the plungers, the conveyors, all these systems are connected with this PLC. And this is the Mitsubishi Melfa 4 LV robot, where it has a 4 kg payload. Similarly, we have 4 setup for training the students, and this is totally a dismantleable and connectable facility. This total system can be dismantled and assembled. Right now I've dismantled some parts to show you how this efficiency will be working on. We will be having different kinds of parts which is located over these 4 cylindrical parts. These 4 cylindrical parts, the plunger will be keep on plunging each and every part. Each and every part will be having different colored, different numbered cylinders, which will go through this conveyor. This is the rail conveyor. Once this rail conveyor, the parts are going in, we have a QR code sensor and the RFID sensor over here. This RFID sensor will be sensing the products, and it will be giving feedback to the robot on which color or the which numbered part is coming on. And the robot will be sensing on which part to be picked up and which not to be picked up. And here is the sensor. Excuse me, here the sensor which will be calculating the speed at which the process is moving on. From this conveyor, it will be transferring to the rubber belt, where the process products will be moving into the rubber belt. And the robot, it's a 2-fingered pneumatic supported robot. These 2 fingers are the closing and opening are supported by the pneumatic compressor. And we have different kinds of gripper support. One is for mission vision cameras to check the quality of the product and the connectivity. The next is for suction, and another one is for the other process. Whichever we are required to, we can allot for that process. So like this robot will pick up the object and keep the object in a required bin. After the required bins has been assembled, the quality check will be carried out using the cameras, and we have a HMI where we can calibrate the products through this HMI, whether which is the right product, which is the wrong product, which can be calibrated in this HMI. And through the surround system, after the HMI is calibrated, the products is verified. If the product is okay, it will be carrying it out to the bin, and it will be keeping in the storage location. If the product is failed, it will be processing back to the waste bin. This is what the basic setup what we have in our facility. And later to the session, I will be teaching how to handle this robot and how these robots have been working on. And before that, we have been keep on telling the concept called teach pendant. This is actually a teach pendant. And once I get back to the laptop, I will be show you how this teach pendant will be working on, what are all the nomenclature of teach pendant. While I'm operating with the teach pendant, I'll also show you how this robot is moving in relative with the teach pendant. This is all we are going to see in the forthcoming sessions. And I will get back to the sessions and come back to you. Thank you. Thank you. Yeah. Right now, what we have visualized is the industrial automation facility which we have in Chennai Institute of Technology. This industrial automation facility, if you take why we call it as industrial automation facility, is because this is a whole setup where you don't need any human interventions to work on with. And this automation, industrial automation facility supports zero human interventions till the start to end of the program. I cannot run the whole program right now because it is unprogrammed right now. So I'll be just showing you how these robots are moved and how the connections are done, and how to operate this robot using a teach pendant, how to operate a teach pendant, and what are the contents in the teach pendant. Everything I'm going to explain to you. And later to that session, we'll be just trying to demonstrate this robot which is behind me with the teach pendant in the hand. That is what we are going to do. And meanwhile, I'm going to go for the slide presentation. Just a minute. Yeah, this is the type of robot which we have in the most of the 6-axis articulated robots, which we call it as joint arm articulated robots. We call these as joint arm because each and every link is connected to a servo motor which works like our hands and arms, which have the similar degree of rotation and similar degree of kinematics available in the robots in relevant to the human beings. Even ahead of the human beings, these robots have much more degrees of freedom. And now in this slide, you can see how these manipulator is consist of the joints and links. You can see the links and joints are mentioned in this slide. Robot manipulator is basically consist of two sections. One is body and arm, and another one is wrist assembly. Body and arm is till the end of the arm. You can see all the orange color part, we call it as body and arm. Up ahead of this body and arm, we have the wrist assembly. Wrist assembly is for end of tool application. Whatever the robot is coming in, if you are purchasing a robot from any company, it may be Kuka, it may be Mitsubishi, it may be Yashikawa, whatever the robot is into. Whenever we are buying the robot from the company, we will be getting the robot similarly what you are seeing this slide. You take for any application you are buying, the robot will be in the similar shape, similar. It can be scaled up or scaled down. The size may differ according to the payload, but the robot looks will be similar. Similar. The 6-axis giant arm articulated robot will be similar. According to the application, it may be your spray painting, building, packing, palletizing. What may be the application? The end arm tool can be changed according to the application. It can be implemented into straight away into the object. That is what this is used in for. And we have seen about the types of robots and etc. Right now we are going to go into the programming of robot. Robot programming is nothing but we are going to teach the robot for desired motions, and the robot may be performing the similar motions after the programming is done. Identifying and specifying the robot configuration. The robots can be in different coordinate they can use different coordinate system. In general, we'll be knowing this X, Y, Z using the world coordinate. It defines the X, Y, Z and A, B, C. It is according to the programmer who is standing in front of the robot. According to us, if we are standing in front of the robot, we can use this X direction, Y direction and Z direction, and rotation of X, rotation of Z and rotation of Y, which is the 6 axis, which we call it as world coordinate system. X, Y, Z and ABC in KUKA, J1, J2, J3, J4, J5, J6 in Mitsubishi, and it depends upon different nomenclature for different robots. That is where with this world coordinate is going to. The base coordinate is nothing but when you are erecting the robot and you are going to install the robot, there will be fixing a base for the robot. According to the base, it depends upon the program depends upon the base. For example, if I am facing north direction, but the base is in the south direction or east direction, the program, if you are keeping in base coordinate system, the program will be starting to run from the east or west direction, not in the north direction. That is what the base coordinate. The joint coordinate system is nothing but each and every joint you can relate with. You can specify you are going to start your program with A joint or B joint or any motor. The servo motors are engaged with each joint. So if you are connecting with any one joint, it will be considering as its home position, and from there it will be calculating the X, Y, and Z direction. And tool coordinate is basically with the end arm tool. Whatever tool you are going to add it, from the tip of the tool, it will be calculating the X, Y, Z and the rotation direction. So it is called as tool coordinate. So these are the types of coordinate points from where this robot is going to take the home position, from where the program is going to run. For example, if I'm starting the home position for base coordinate, the coordinate 0, 0, it will not be same for all the other coordinates. It will be in the 0, 0. It may vary. So that is what the main concept. And for the programming methods, there are different types of programming methods. First one is manual programming. It is which we have in our institution. We have to take the robot pendant, and with that pendant you are going to operate the robot and you are going to record the points. The robot is going to keep on repeat the recorded points. That is what the manual method. The walkthrough method is the concept which is used in the cobots, collaborative robots. Collaborative robots are nothing but it is a human-friendly robot where you can move the robot arm using your hands. It won't be any restrictions will be there. You can move your robot arm with your hand, and you can stop it wherever you want, and you can record it. From there, you can take it to some other point. You can record it. This is what the walkthrough method of programming. Lead through method is nothing but where the online programming is collaborated with the walkthrough method. That is where lead through method. And the OLP is nothing but offline programming. It is somewhat efficient because you can simulate it in the system and you can incorporate to the robot. Unlike the manual method, you directly have to operate in the robot. In the offline programming, you can record it in the system and you can incorporate it to the robot. That is what the offline programming. Here is the difference. That is in online programming, teach pendant and lead through programming are under online programming. Robot programming languages and task level programs comes under offline programming. Robot programming languages, it is nothing but it depends upon to each and every robot. For example, if you take KUKA, they have KRL, KUKA robot language they have, and they use software called Simpro, KUKA Simpro 2.0. They right now it is running on. They'll be using it for. If you take this Mitsubishi Melfa robot, this Melfa robot uses the ladder programming, the basic PLC ladder programming. The similar ladder programming is used in this Melfa robot. So each and every manufacturer will be having their own robot programming. It depends on how they use it and what they use it. And yeah, this is a kind of online programming from KUKA. I can explain you very clearly. this programming takes very detailed understanding. If you understand this set of 15 lines of program, you can easily program software for yourself itself. Before going into this part, I am going to explain you about the basics of the movements which is available in the software, the KUKA robot language software. Basically, in the KUKA robot language software, we use three major movements. These three major movements we call it as PTP, which is nothing but point to point, and second one is LIN, which is linear. The third one is CIR, others nothing but circular. These are the three major commands which used in for the programming. This programming is comes under this three lines or three different commands in programming. Is totally, you can program any kind of complicated programs also with this three commands. First one is point to point. You can easily understand if I'm starting my point in 0,0 and I wanted to reach my point in 2,2. There are any number of ways, n number of ways to reach this 0,0 to 2,2. So the robot, according to its kinematics and according to its joints, it will reach this 0,0 to 2,2 in any way. You cannot justify or you cannot understand in what way the robot is moving. If you want to understand it, you have to do a detailed research process on how the robot is moving on. It actually moves in a kinematical arrangement which is the easiest path to reach to 0,0 to 2,2. If I ask any person to understand what is the easiest method to reach a point to other point, you can easily tell it's just a straight line. If you draw a straight line, you can easily, that is the shortest distance to reach any 2 point. But according to the robot, which is the easiest point in the sense it depends upon what is the kinematic arrangement or what is the position which the robot is standing on to. So that is what this point to point command is. If you take any point from this to this, it is not that it want to reach the point from this way. It can reach by this way or it can reach by it depends upon. So that is what P2P. If you don't want to reach the robot in a straight line, if just you want the robot to come to one point to another point, the robot may take any position, you can go on with PTP. That is point to point. The second one is linear. This is what we usually do. Go in a straight line. If whatever the point is given, go in a straight line. That is this linear command is. For example, if I'm positioning a point in 0,0 and I want to go to the point 2,2, it will travel via 1,1 in a straight line. That is what this linear is all about. And all these commands, the linear and PTP uses only 2 points, the start point and end point. Unlike the circular command uses 3 points. Actually, the 3 points is start point, auxiliary point, and end point. So it uses 3 points. Why is in a sense that the second auxiliary point is the curvature for the first point and the third point. It will go via the second point in a curved manner. That is where this circular interpolation is used into. So the start point and end point and auxiliary point, all the 3 points should be implemented. If you're running in a program, in between, if the circular command is coming, the start point will be considered as the previous line's end point. For example, if I'm using 15 lines of program, if circular command is coming in 14th line, 13th line endpoint will be considered as the circular's first point, and you have to implement auxiliary point and also the endpoint, so that from the 13th point it will take a curve or a circular pattern which is being described, and it will go on with the movement. These are the 3 important commands which are going to be worked in the robot: the start point, end point, and the point to point, linear, and circular. Now we will be moving on to the program part. This is the actually teach pendant. I took a snapshot of the teach pendant. This is how this teach pendant will be looking like. And inside the teach pendant screen, these are the commands will be there. This command section I will be taking a walkthrough at the end. Before that, we will be understanding the program. there is lines you can see 1, 2, 3, 4, 5, 6 till 15. It is not that this program is till 15. We have a lot more program in the session. We have just constrained you for the first 15 lines over here. The first line is given as INI. It is the initial programming line. Actually, when you start the program will be in such a way that 1, 2, 3, and there will be next line 5. That is where if you take any program in KUKA, the 1, 2, 3, 4, and 5 will be always determined pre-written. You don't need to write these 5 lines. The initial line will be common, 2 will be empty, 3 will be PTP home. Wherever the point is, wherever the robot is, it has to reach the home position. Home position of each robot and each organization may vary. For example, in the previous session, if you have attended, you would have known I've shown the robot in an compressed a compressed situation where all the arms are bent and it is like a small object, the prototype of the robot. That in such condition only from the manufacturers, it will be going to all the vendors or the applicants as a home position. The home position of each robot will differ according to the requirement of the application. So in Chennai Institute of Technology, we have our home position for each robot in a different manner. It's according to the application what we want, or according to the environment what we are looking like into, we can change the home position. So the program's first line will be based on wherever the robot is, whatever the robot's constraint is, it should come to the home position. For example, if the previous programmer left the robot in some other position or some other area, you no need to program it or jog it to drag to the original position. If you click this line and enable, it will straight away come back to the original position. And the second one is, and the second last line will be home position. The fifth line will be home position. So before the fifth line, you can keep on inserting n number of lines you want to program for 300, 400, 500 lines of programming. You can keep on interpreting, and finally there will be a called home position. This is so-called online program because we straight away use the teach pendant to train the robot. That is what the online program is all about. And you can see this program right now. We have given PTP, point to point. And P1, we are going to select point 1. We are going to record the point 1. How we are going to record it? You're going to jog the robot using the teach pendant, and you are going to keep it in some place, and you are going to record that point. And before going into this, you should understand what is this enable, how this robot is moved, everything. So I'm going to take the teach pendant and I'm going to show you from here how this teach pendant will actually look like. I'm not going to use the KUKA. We have the facility of KUKA in the next laboratory. Right now I'm going to show you the facility with the Mitsubishi facility which we have in industrial automation. I'm going to take the teach pendant of Mitsubishi and I'm going to show you the nomenclature of the Mitsubishi teach pendant as well as how this robot can be moved using the teach pendant. Just a minute, I'll be coming back in online, taking the teach pendant. Yeah, sorry for the interruption. And in my hand right now, I have the teach pendant of Mitsubishi. This is how the Mitsubishi teach pendant will be looking like. And I'll be getting you through the whole setup. Here we have a light. Here we have some yellow color stuff. I'll be explaining all this stuff, what all these stuffs are. And as I shown in each, whatever the robot manufacturers are, they will be having one emergency switch in the controller. And you can see the one more emergency switch which is available in the robot, and there will be one more emergency switch which is in the controller also. These three emergency switches are mandatory. And I think the screen will not be that clear because It is not a touch pendant. It is not touch pendant. It is totally keypad based pendant. This program in this robot we used to do an offline programming. You can do the programming in the computer. You can incorporate it into the robot. That is kind of program you use in the manipulator. And if you have any queries, please post in the session so that I can answer those questions also meanwhile. And if you take this pendant, the first and foremost thing you have to understand is how to handle this pendant, how to hold this. You're going to hold this way, or you're going to hold this way, or how you're going to hold this. First thing is you should, because programming in a robot will be taking a longer time. So you have to handle in such a way it should not harm you. So there is a way for you to leave your fingers, and your thumb fingers will be accessing the keypad, and all the other fingers you have access to work on, which will be free in the free to hold in the rear. It is not very heavy. It will be around 100 to 150, between 100 to 150 grams, not more than that. It is very lightweighted. Since it is non-touch pendant control Mitsubishi, it is very light. If you take KUKA, it will be around 400 to 500 grams. It will be a little bit heavy, and it has a different holding style. So holding a pendant, this pendant which can be holded this way. This is the way to hold this pendant. And we have a switch called enable switch. This switch, if you press it out, it will go off. If you press again, it will come in. This is the enable switch. And we have an enable key over here. This enable key is very important key, where it actually is like if you want to operate anything without this key in this robot, it is not possible. This is very important key. This enable key. This enable key, I will show. Bring my mic nearer to the enable key. You can hear different sounds. It is very important to understand these sounds. If you see, I can move this enable key this way or that way. You can see a small sound. You can see this. I think you can hear the small sound. This is one sound where this enable key is in action. If this sound clicks, it is in action. If I'm keep going into the severe, okay, right now I'll show you two different sounds. It will be coming. Just listen to it carefully. I think you would have heard this two different sounds in the teach pendant enable key. This is why, because this is actually one of the most safest method to handle this robot. If you what is the purpose of this key is, if you hold it in a middle position, you should not hold it loose, or you should not hold it tight. It's a middle position to hold it. If you hold in this middle position only, you can able to work anything in this robot. If you are not holding that position, the robot cannot be worked in. The robot will not work. And if you lose it, for example, if you're losing it for a strain, if your hands are straining or anything, if you leave it, it will not work. Or if you are not understand whether you are pressuring it in a good range, if you hold it very tight also, it won't work. This is the utmost safety which is given by any robotic manufacturers in the teach pendant. Why? That is why it is because if you work with a robot, as I said before, this robots are very heavy, and it can move in a very high velocity, and the damage which can be caused by the robot is very high. If it is damaged, it will be very high. So once the person who are handling with the robot is having the teach pendant in his hand, like he has this remote control of the robot with his hand. He can do whatever he want with this controller, this teach pendant. So he must have some kind of consciousness to work with it. So what will happen is, when you hold it in a middle position, you will be always in a conscious state to work on with the robot. If a person who is working with the robot is sleepy, what he will do, he will just leave the pendant. Or if he is facing any kind of fear or anything, he will tend to push it back very heavily. So whatever the scenario is, it will tend to lose the circuit, and it will break the circuit, and the robot won't move. Actually, there is a automotive company which uses the similar technology in their acceleration pedal. You know, the companies like Audi or Porsche. So these company uses this kind of technology in their high-end cars to avoid accidents. What will happen is the driver in India, if you take this scenario, we won't drive for longer distance with the car. We used to travel maximum of 400 to 500 kilometer in a stretch. Not too in a stretch, we will take breaks also. But in case of foreign countries like USA, Germany, they used to travel longer distance, like miles together, in a single stretch using their vehicles, cars. They won't have this geared stuff. They will be having automatic stuff, and they will be having cruise. There's a concept called cruise. When your acceleration pedal is done, if you put it on the cruise, it will be automatically moving on. You don't need to push anything on efficiently. If not in the cruise control, if the driver is pedaling his acceleration and there is some kind of issue is happening, for example, if the driver is slipped or the driving person is slipped, what he will do will suddenly he will take off the acceleration pedal. If there is a scenario, there won't be a big deal. The car is going to stop at some point, or it will get slowed down. That won't be an issue. But you see, when we face accidents in India, most of people would be faced accidents in two-wheeler or four-wheeler. Not in a big stage also. At least you would have felt the adrenaline rush when you go near some vehicle or you go near some person. What you do is gradually what we should do is we should apply the brakes, or you should apply the brakes in the hand. But what we will do unconsciously is that we'll apply the pressure on the acceleration pedal rather than the brake pedal. It happens. Actually, it happened to me also, but somehow, God grace, I've controlled it somehow. But if the acceleration is pressed heavily, what will happen is again the vehicle is going to rise up. So to avoid it, what they did is the same technique. If you press it in the middle and the conscious state, it will move. If you release the pressure, it will cut off, or if you really put the more pressure on the pedal also, it will be cutting off. This is what the technique they have followed in this teach pendant also. Just a minute. Yeah. This is how this teach pendant will be working on. I think I've explained the teach pendant to the extent, and right now I'll move on to the programming part, how this programming is done. The first line is PTP. I'm going to use this teach pendant kind of stuff. This is not the same teach pendant. This is the KUKA teach pendant, which you're going to see in the slide. And in my hand, I have the Mitsubishi teach pendant. With this teach pendant, I'm going to move the robot to one position called P1, whichever the point it may be the coordinate. It's not based on the coordinate. It is based on the tool wherever which is working on. I'm going to travel the point to PTP1. And velocity I'm giving it as 100%, and the tool is 16 and gripper base is 29. The tool is 16 and gripper base 29 is nothing but where the tool and base is calibrated. For example, my robot, if I'm, as I said before, if I'm facing the robot in the north, I'll be fixed as tool is 16, tool is gripper, and base is wall. But if some other person is coming on, if they want to work on with another dimension of the robot or another direction of the robot, they will have to change the tool and base number. So if they change the tool and base number, the tool and base will be calibrated to that end, not at the previous one. So that for each and every program, if you have to fix the tool number and base number, once you are fixing the tool number and base number, for all the program, it will be automatically coming. What you're going to do is you are going to click motion. There will if you see in the bottommost part of the slide, there will be a command called motion. If you click that motion, it will be automatically coming in PTP. What point you are? If you are in the point 4 will be coming on. If you are in the point 2, the point 2 will be coming on. Automatically, these lines will be pre-written. What you're going to change is you will be having a option to move on with. If you want to go with PTP or linear or circular, you can select it. And the velocity, you can select it. You can add the velocity from 0 to 2 meter per second, or you can reduce it. And all the other details will be predefined, because when you're starting the program, you have to mention what is the tool number and what is the base number. According to the tool number and base number, it automatically rearranges and it will be keeps on moving into. That is what the concept of the tool number and base number. And you can see different kinds of the lines have been comments have been given in for. First one, they are given PTP, and there is linear in the 6th and 7th line, and the 9th line they are given circular. Circular, you can see the P5 will be the start point, and P6 and 7 will be the auxiliary point and end point. I've mentioned it before. For linear and PTP, you need only 1 point. From the previous point, it will be reaching to the next point. But in case of circular, you need 3 points. The previous point is first one, the auxiliary point is the second one, and the end point is the third one. So you need 3 points to reach the circular. So that is what mentioned here, and this is how a normal robot program of KUKA will be looking like. For each and every program, they have their different style of programming language, and but mostly it will be similar. Not everything will be similar, but mostly there will be similar programming which will be adapted in the robot. And the next part is going to go for offline programming, which is done in the software and which will be incorporated into the robot in the later part. Whether after the checking process done in the end of this is manipulator, I mean the simulation part, then later it will be to carry forward to the robot. Yeah, this is the programming, offline programming, which is enabled in KUKA software using KUKA Simpro. You can see the similar robot which we have in the facility is predetermined in the software. The software will be having all kinds of robot. You take any kind of robot, any kind of gripper, you can incorporate from KUKA, which can be incorporated into the software, and the software can be used to simulate the programming which we done in the online mode in an offline mode also. Before after this programming is done, we have to once again go on with the programming part into the online. We have to check it in the T1, that is the teaching mode 1, where the maximum velocity is 10% of the full velocity. So with that we will be checking it on. Later that we will be going for T2, we will be slightly increasing the velocity, then we will be checking it, then finally we will be going in for automatic mode. So this is the method we are going to one by one to the each and every concept. And this is the programming which we used in this Mitsubishi Milfa 4LV 4FLD, and it is basically done in the software, and it will be incorporating into it. And this is how this different types of programming is done in the different programming parts. If you have any doubts in the programming part, you can comment in chat section. I'll be going through it and I'll be explaining you the different types of programming. And if you have any doubts in the programming also, I'll be explaining it. Okay, I'll be moving on with the session with the next part, which is automation. And if you take this automation setup, there is a lot of different methods which is used inside the automation. What I've shown you over here is also a part of automation, where we use here to differentiate different kinds of cylindrical objects, different colored cylindrical objects into a certain restriction pathway, and we collect the different parts and place it in a container. We close the container, we do quality inspection, and we place it in the bin. If the waste products are, we will be put it in the waste bin. This is what the concept which we do in our facility. If you take this similar facility in the any other big concern, manufacturing concern, from the raw material to end product, how a product is going to be delivered and how a product is going to be transferred from the raw material to end product, you need or AGV, you need your conveyors, you need robots, or you need human interventions to work on with. All these stuff will be incorporated. So all these stuff together, we call it as a process called automation. So this automation process doesn't deals with any robot, single robot, or any single microcontroller, single PLC, nothing like that. It actually involves multiple operations or multiple machineries to engage to work on with a single operation is called as this automation. And I'm going to show you a small video which will be showcasing the automation facility, which you are going to understand how this automation is available in the other facilities. I think most of you is aware of Amazon. Amazon is a company where it uses many numbers of its employees to work on with, and I'm going to show you this Amazon's warehouse, how this Amazon warehouse is working on with, and how efficiently this Amazon working warehouse utilizes automation to its fullest. That is what we are going to see right now. Just a minute, I'll be linking to Amazon video. Yeah, it's right next to us. We will see this video and we will come back to the session in a while.
Amazon is the world's biggest retailer, and its CEO Jeff Bezos is the world's richest man for one very good reason. His company is better than anyone else ever at giving people what they want quickly. Amazon acquired its undisputed status as the heavyweight champion of the retail universe thanks largely to its lightning-fast delivery times. The astonishing feat of ferrying hundreds of millions of items, from guitar strings to saucepans to car parts, directly to your door inside 24 hours is nothing short of a modern logistical miracle. So how does Amazon do it? A super smart army of slave robots, for one. Ingenious, if occasionally unscrupulous, management practices are part of the answer too. And the modern-day voodoo of deep learning AI, all of which are made flesh in the most advanced stockrooms the world has ever seen. So join us today as we button up our high-vis jacket and journey inside Amazon's smart warehouses. In the year to September 2020, with the global economy in the teeth of coronavirus and the bleakest employment outlook in history, Amazon reported global revenues of little under $350 billion. That's roughly double what it earned in 2017, by the way, only 3 short years earlier. Not bad for a company which only started trading in 1994. Amazon has built its empire on a platform of sheer, unbeatable convenience for the end user. You, the customer, need a product. So you open the app or have a quiet word with Alexa, and next day, hey presto, it's sitting on your doorstep. Moving products from A to B quickly is not easy. Compared with other modern technology giants which barely need to exist in the real world, think of Netflix, Google or Facebook, Amazon needs to shift an astonishingly vast amount of sheer bulk safely, precisely and quickly all day, every day. So how does it do it? Last year, a senior Amazon executive described Amazon's warehouses, rather poetically, as a symphony of humans and machines working together. How does this symphony actually work? Let's take it from the top. Before you've even logged onto its website, Amazon has a fairly good idea of what you're going to buy. This is all down to the semi-occult 21st century abracadabra that is deep learning AI, which Amazon has been leveraging to incredible effect since around 2015. Put simply, an algorithm makes some assumptions about you based on your age, location, socioeconomic background, and purchase history. It will then, hours, days, or even weeks before you actually log on, ensure that your local warehouse is stocked with appropriate quantities of stock you're likely to consider buying. This might be a certain style of racy swimsuit that the algorithm anticipates will be the hot new must-have come springtime. It might be the paperback novel for a soon-to-go viral TV adaptation. In January 2020, for instance, Amazon's algorithm correctly anticipated high incoming demands for face masks, and, well, we all know what happened there. So Amazon's smart warehouses, also known as fulfillment centers, not to be confused with their post office-style sortation centers, very often know what you want even before you do. Or at least they know the very second you click buy now in the case of those wine-inspired late-night impulse buys. Once you've clicked, our symphony begins in earnest. You may have read headlines in recent years suggesting Amazon workers walk as many as 12 miles per shift, darting about between shelves, frantically picking up items. That's no longer quite true. Amazon's modern fulfillment centers are largely patrolled by an army of squat, Roomba-like robots that pick up whole shelves, also known as pods, and bring them to a human picker situated at a stationary workstation. Amazon's enlistment of this whirring battalion began in 2012, when the company purchased robotics company Kiva Systems, the market leader in warehouse automation, for an eye-watering $775 million cash. The company's flagship model, commonly referred to as Kiva, is around 30 centimeters high and capable of lifting 450 kilograms in weight, whilst traveling at around 3 miles per hour. The substitution of these squat orange automatons in place of dashing human workers makes a colossal difference to Amazon's bottom line. It's been estimated that Amazon's warehouses can now hold 50% more stock and retrieve that stock 3 times faster. This reduces the overall cost of fulfillment by some 40%. Cheaper, quicker warehouses mean products that are more affordable for the end user, and crucially, products that are much more likely to be on the van driving down your street the following day. Amazon isn't about to stop there. In a move that could be described as either ruthless or inspired, upon purchasing Kiva, Jeff Bezos changed the name of the company to Amazon Robotics and told all previous Kiva customers, household names like Gap, Walgreens and Staples, they'd no longer be allowed to buy new Kiva technology. This, of course, gives Amazon an incalculable competitive advantage. Since rolling out the Kiva robot across its fulfillment centers, by 2018 they had 100,000 of them, by now that figure has comfortably surpassed 200,000, Amazon Robotics has been refining the design still further. The new iteration of Kiva, known as Pegasus, is 10 centimeters shorter, meaning more can be stocked on top, and uses half the parts, so it's cheaper to manufacture and maintain. Amazon says Pegasus can lift a hefty 600 kilograms and can be customized with a conveyor belt to work in the sortation centers, where, Amazon reports, errors in delivery have been halved thanks to Pegasus. Naturally, Amazon isn't quitting there. Last summer it announced a newer, thinner robot still, called Xanthus, and coming to a fulfillment center near you. So how do these pimped-out Roombas get around without knocking into each other all the time? Cloud-based software, operating what can fairly be described as an AI-run air traffic control network, coordinates the route of every single robot. This is all about optimization. What's the quickest route to get to a product that won't interfere with other robots on their own runs? What's the optimum speed, acceleration, and deceleration? As many as 800 robots can be deployed at any one time on the warehouse floor, although in practice, the numbers tend to be kept lower to avoid traffic jams. When their batteries run low, the robots are instructed to find the nearest charging station. Since robots took over the warehouses, changes have been implemented to improve their working conditions. Skylights, for instance, are now covered up, so the robot's sensors aren't confused by glare. Air conditioning units that blow downwards in areas where humans work now blow sideways so as not to topple delicate items from the tops of moving shelves. To navigate, a camera on the robot's undercarriage reads QR codes embedded in the floor, and individual sensors help the robots slow or swerve to avoid obstacles in their paths. Compared with these scurrying warehouse servants, some other robots working at Amazon look almost humdrum and conventional. The so-called Robo-Stow robotic arm, for instance, wouldn't look out of place in an old-school car factory, except it can lift a hefty 1,200 kilograms and manipulate shipping pallets to within 1/10 of a millimeter accuracy. There's also the labeling robots, nicknamed slam machines by human co-workers for their relentlessly percussive racket. These can label up to 1 package every second. And for a hint of what'll happen in the coming years, Amazon recently purchased Canvas Technologies, a firm specializing in autonomous robotic carts. Just picture the most sci-fi drinks trolley you can imagine. Robots, of course, are only part of the story inside Amazon's smart warehouses. Even the company's most fervent futurists admit the notion of complete automation is a decade away, and even then probably won't happen. So what of the human side? Amazon's management techniques, in concert with all that automation, have made the business astonishingly lean and mean by historic standards. In 2016, it was estimated that by bringing everything in-house, as opposed to all the duplication inherent in a standard high street or shopping mall, Amazon requires only half the employees a traditional retailer might, per $10 million in sales. What are all these humans, hundreds of thousands across the world, actually doing then? Well, since Kiva and its robotic heirs took over, there's much less rushing around than there used to be. But there's still plenty of tasks requiring dexterity and problem-solving. The 2 most common roles still done by humans are stowing and picking. When goods arrive at the fulfillment centers, they're stowed by humans onto shelves or pods to be collected later by the robots. The pickers then pick the specific item from the shelves when the robots come by, then send it on to be packed. Workers on the picking side are encouraged to work fast in order to maintain their so-called rate. If workers' rate falls below expectations, employees can be disciplined and ultimately sacked. According to one ex-employee, this rate can be challenging to fulfill. 120 items per hour when they started at the company, rising as high as 280 items per hour just 3 years later. Errors are also punished. According to the same ex-employee, workers were once permitted 1 error per 1,000 items, but now they're only allowed 1 per 2,200. The rates only get more challenging during Prime Day when sales on Amazon skyrocket. One way Amazon encourages workers to make rate is through gamification, or making the whole thing into a game. So instead of a plain old-fashioned graph telling workers where their productivity stands in relation to the rate, workers instead play and compete on in-house games with names like Pix in Space, Mission Racer, or Castle Crafter. So essentially, the faster and more accurately employees pick stock, the faster their little pixelated car moves around the track. Other incentive schemes, such as in-house currency swag bucks, reward hard work with Amazon-branded merch such as water bottles or t-shirts. Amazon has regularly found itself in the firing line for its intense working practices. According to reports, as many as 14,000 serious injuries occurred at Amazon sites in 2019, a per-employee rate of nearly double the industry standard. Deaths are infrequent, but not unheard of. In the UK alone, during the 3 years to 2018, ambulances were called to Amazon warehouses 600 times. For its part, Amazon is keen to stress it invests tens of millions of dollars into worker safety awareness programs, but there's no denying injuries spike around Prime Day. So are Amazon's ultra-efficient warehouses ultimately a force for good? While COVID-19 laid waste to vast swathes of the conventional retail landscape, this year Amazon has been processing up to 40% more orders than expected. In the month leading up to March 23rd alone, toilet paper sales increased 186%, sales of cough medicine skyrocketed 862%, and children's vitamins went up 287%. Plainly, in a world where going to the shops can be a risky business, Amazon is fulfilling a need, and as such, ever greater numbers of people are relying on it. Will the robots steal our jobs then? The outlook is unclear, but within Amazon, it's plain to see that humans are still needed for many aspects of the work. And even if robots can one day stow or pick as fast as humans, dealing with mini crises like leaking paint pots on a fast-moving conveyor belt or identifying ripe bananas on site will still need the human touch for some time to come. Whatever the future brings, Amazon's new $40 million robotics lab just outside Boston, for instance, or its tantalizing patent for airship-like floating fulfillment centers, one thing can be guaranteed. As long as we're all buying, Amazon will keep on delivering.
So before going into explanation of the automation process, we are just now going to see a small demo on how this industrial automation facility works on. Just going to, with the help of Mr. Karthik sir, we are going to understand how this facility is going to work on CIT. I will now turn my camera to the phone and I will be connecting you over there. Yeah, right now we're going to enable the teach pendant and the facility is going to work on with. I'll just go just behind to simultaneously show you how this robot is working on with the working process. Yeah, it is right now they are using the positive and negative movements of the base motor. Now we are going to move the second joint to work on with. Joint 2 has been utilized to move on. Now they're going to use the joint 3 as joint 4. I'll go closer to understand you how this robot moves on. Yeah, that's it. Actually, the moments is